Good evening, everyone. My name is Nyla Duhan, and this is Surf X. A man by the name of Neil Armstrong once said, "One small step for man is one giant leap for mankind." When Neil took his first steps on the moon, he was going where no human had ever dreamed of going before. His first steps were cemented not only on the moon's surface, but throughout history forever. The only thing is, the moon is only one of billions of celestial bodies in our galaxy. Thus, why should we only limit ourselves to the nearest orbiting body? After 50 years, humans are more than ready to explore space and celestial bodies outside of the moon. For one, whether it's in a Milky Way bar or the collection of billions of stars of the same name, exploring space allows us to find our place in the universe. The universe is ever expanding in either direction for eternity. Thus, being able to find our place among other bodies and systems that may also contain life or living organisms is a must. Along with life, with any major excursion, the development of new technology not only benefits off planet exploration, but also any on planet discoveries, considering the thousands to millions of things created for each space shuttle launch with only one function in mind. This technology can be used to collect material samples, search for signs of life, find future habitats, and honestly, are about as cool as Ryan Reynolds. But as fun and exciting as all this sounds, how do we explore space? How do we go from Earth to any planet in our solar system? In the past, to explore space, there's been a myriad of methods used to investigate the unknown. Using the International Space Station as a base, scientists have sent telescopes, probes, and flybys to conduct initial space missions and gain information and resources needed for manned missions such as the Apollo 11. However, as of the last 20 years, the most popular method of exploration has been the rover, or as we refer to it today, the Space Explorer. Our Space Explorer, or SURFX, will serve as the next step in space exploration. With it being much too early to launch manned missions, the SURFX is the exact product that will accelerate our understanding of our neighbors tenfold. The SURFX is the ideal configurable space explorer in that it is perfectly capable of exploring nearby planets without risking a single human life. From the safety of Earth, the SURFX can travel the surface of new planets looking for life, sending information back to mission control, all while being deployable, adaptable, and most importantly, affordable. I will now pass it over to Micah to talk about the stakeholders in the general overview of our product.
Thanks, Nyla. With the capabilities and configurability of the SURFX, NASA stands as the primary stakeholder. Integration of the SURFX across NASA missions could significantly reduce project design phases and costs, which currently require significant resources. Of course, private space companies and other space agencies pose to benefit from the SURFX too. The SURFX's main objective requires it to be low cost and modular with broad exploration capabilities. The main objective feeds into our project needs. The SURFX will cost no more than $10 million, ensuring that space exploration and discovery are more accessible. It will be no more than 50 kilograms and be able to carry a scientific suite of instrumentation of 20 kilograms. Navigation in rough terrain and being able to operate in a low gravity environment allow for the SURFX to explore as many places as possible within the solar system as we can manage. With such a broad range of possible destinations for the SURFX, both autonomous and remote capabilities are required. And lastly, the ability to communicate the scientific data collected is one of the most important parts. While these aren't required, a lifetime of over an Earth year, being modular, and cost efficiency are key aspects to the success and scalability of the SURFX in the space industry. As a surface explorer, the SURFX will have design and mission elements similar to rovers sent to both Mars and the Moon. While the Mars rovers were designed with explicit requirements and exclusively for Mars, the SURFX will have similar features. The United States sent the Sojourner in 1996 and then the Spirit and Opportunity in 2003, which cost $1.2 billion. While this cost includes launches and technological development and is not exclusively for the vehicles, it does demonstrate the cost barrier to exploration. The Curiosity was sent in 2011 and has traveled over 28 kilometers of Mars terrain. The Zhurong, a Chinese rover, features a suite of scientific instruments and a high-resolution camera. And the most recent Mars rover, the Perseverance, has 7 custom scientific instruments and a helicopter. Lunar rovers also provide significant insight to explorer design, especially with designs for power and maneuverability. China sent the Yutu-1 to the Moon in 2013, which operated and collected data until 2016, and then the Yutu-2 as a successor in 2018. The Soviet Union sent Lunokhod-1 in 1970, and it was the first rover successfully sent to another planetary body, and then the Lunokhod-2 in 1976. Next, Anna will reflect on other relevant examples to the SURF-X.
Thanks, Micah. My name is Anna Jung. In this slide, we're going to talk about some of our relevant conceptual examples. The first example being CubeSats. CubeSats are a type of nanosatellite. CubeSats use the standard U dimensioning of 10 centimeters by 10 centimeters by 10 centimeters. Because of this dimensioning, CubeSats are small and light. And because they're small and light, CubeSats have reduced launch costs. CubeSats are also made with off-the-shelf components. Components you could find from your everyday online retailers like Micro Center, Amazon, and many more. Our next conceptual example is personal PC builds. Personal PC builds are often built to the exact needs and budget of the builder. For example, a $500 budget might not get you the best components, but a $2,000 budget would get you significantly better components. About personal PC builds is that components are built with assembly in mind. Components are assembled together rather than forced to fit together. Our final conceptual example is cars. The machine, not the movie. If you've ever bought a new car, you know that there's the base model, and then there's the higher end, more luxurious models that have things like leather seats, seat warmers, in-car navigation. If you have a BMW, you might need a subscription for those seat warmers. But the idea of a cheaper base model with optional additive features is something that we would like to implement into our preliminary design. Additionally, the do-it-yourself mechanics of a car, things like changing the oil, checking your tire pressure, are things we would like our consumers to be able to do on our product. Doing the metaphorical changing of the oil on our rover. Here is the concept of operations for our SURF-X. In the first square, you will see the carrier land on the planetary surface. In the second square, the carrier will open its doors and the SURF-X will deploy. In the third square, the SURF-X will begin its startup sequence, which includes boot up and rotation of solar panels to the sun. In the fourth square, the SURF-X begins normal operations and communications with ground control. This image shows the concept of operations for our SURF-X's communications. We have a direct line of communication between two surface explorers as shown by the dashed line. This is so they don't run into each other, to communicate data, rescue one another from a rough spot, or to even work with each other's scientific instruments. To communicate its data back to Earth, the SURF-X must first communicate with the carrier/lander. The carrier will then relay the information to the closest satellite. The satellite will then relay the information back to ground control. To communicate commands to the SURF-X, ground control will communicate with a nearby satellite. The satellite will then communicate those commands to the carrier/lander, which will then transmit the commands to the SURF-X. Next up, we have Terry Thowndale to talk about some of our concept architecture.
At our current phase of development, our concept architecture is mostly focused on our modular system, which will allow us to attach recurring pieces to our rover. For our rover, we're going to use something very similar to CubeSat designs, where they have a U standard, which is a 10 by 10 by 10 centimeter cube. In our case, we will have something similar, which we will license out to other companies who want to use and make their own modules, as well as making our own modules within this framework. We will have the edges be used to make electrical connections, as well as structural connections, as shown in our preliminary CAD file. Given our requirement for a $10 million budget, there were several things we had to consider financially, which is why we actually went for the modular design. Having something consistent like this would lower our R&D, as well as the ability to license out different designs would mean that we could make additional developments, often without having to incur much cost, as many companies may custom make their own modules to suit their own needs. This also allows us to have our base model have only the bare minimum necessary sensors, and final assembly would allow our customization, which we could either do ourselves at a simpler cost or allow the other companies to do themselves. Because we took all of these lessons, and like a CubeSat, which with consistent design can have cheaper launch costs, hopefully this can also be implemented into our launches. And with these universal connections, we won't have to make new solutions later with updates and repairs as we iterate on our design.